4A. Properties of vectors and scalars. 4.1. Defining vectors and scalars. A manager gives a customer directions to her store, 3 blocks north and 4 blocks west of City Hall. The customer's trip can be represented by 2 arrows on a map, each having a specific length and direction. An artillery officer knows that the muzzle velocity of a fired cannon projectile is 930 nm/s. He must raise the barrel of his cannon to an elevation of 33 degrees in order to hit a target. The initial speed of the projectile can be represented by a long arrow labeled 930 ms at an angle of 33 degrees above a horizontal line. An engineer for a tire manufacturing company is designing a new, low-profile, radial tire. In order to understand how the tire will respond to hard braking, he sketches a diagram of the various forces at work on the tire. He draws arrows representing the weight of the vehicle, the road. Large quantities are represented by long arrows and small ones by short arrows. The diagram helps the engineer understand the dynamics needed to create a computer model of the tire design. In each case above, vectors are used to study quantities that have 2 pieces of information, a specific numerical value and a direction. Physicists use vectors to study dimensions such as displacement, velocity, force, acceleration, and magnetic fields. Vectors are drawn as arrows on vector diagrams. Physicists also work with scalars. A scalar is a quantity that can be described completely by only a single numerical piece of information. Time, mass, volume, and temperature are all scalars because, unlike vectors, they have no direction associated with them. Some scalars are only positive, such as mass and time. Others, such as temperature, may be positive or negative, depending on the instant of measurement. A vector symbol is printed with boldface Roman type, A. Since writing boldface letters is difficult, you may use a regular letter with an arrow over it. A arrow upright, lines around the vector symbol, absolute AIE, stand for its absolute value and specify its magnitude. As a shorthand notation for the magnitude, either the italicized letter or the absolute value sign will be used. That is, A, chia, AB, handwritten A or AIR. The symbol TIR means is defined as. 4.2 Vector angles. Vectors and diagrams provide important information. The tail of the arrow can indicate the starting point of motion, or the point at which a force is physically applied. The length of the arrow is proportional to the magnitude of the vector quantity. Vector diagrams also include directional information indicated by the orientation of the arrow. The vector angle, labeled with the Greek letter theta, is given a numerical value in degrees or radians, measured from a fixed direction. This reference direction is usually determined by convention, or is selected for convenience in working the problem. This is especially important in 2- and 3-dimensional vectors. For 1-dimensional vectors, direction can be indicated by a plus or minus sign, as stated in Chapter 3. There are some conventions, generally agreed upon rules, for establishing reference directions for angular measurement. This will be especially applicable to 2-dimensional motion, which you will study in the next chapter. In the Cartesian 2-dimensional plane, the reference direction is the positive x-axis. Positive angles are measured counterclockwise, and negative angles are measured clockwise around the origin. There is no limit to the size of geometric angles. An angle can be measured in either degrees or radians. Map directions are always referenced to geographic north, which by convention is located at the top of the map or diagram. Angles referenced to true north are indicated by a capital T in place of the degree symbol. Map directions are usually measured clockwise from north. For example, 315T is northwest. When using north as the reference direction, angles are always positive and are reported only in degrees from OT to 360T. This textbook will always give map directions using 3 digits, which is standard practice for navigational purposes. In this system, north is 000T, northeast is 045T, south is 180T, and so on. On the other hand, if a problem gives an angle with the degree symbol, e.g., 120 degree, Then you know that a Cartesian reference direction is being used. 4.3 Transporting vectors. Drawing accurate vector diagrams requires a protractor and a ruler. For most physics problems, it is sufficient to sketch the approximate magnitude and orientation of each vector. Unless specifically requested, sketches don't have to be made exactly to scale. Vectors are equal if they have both the same magnitude and the same direction. Examine vectors A and B in Figure 4.8. Even though they are at different locations in the diagram, they have identical magnitudes and they point in the same direction, so A, serifs B. Remember that vectors are models of the physical quantities that they represent. If necessary for the sake of a problem solution, it is perfectly permissible to transport a vector from one location to another in a diagram as long as you maintain its original length and orientation. See Figure 4.9. A marine biologist is periodically monitoring the location of a submerged humpback whale, Megaptera novaeangliae, using a sonic transponder. He plots its position at 3 different times on a nautical chart. The whale's position with time is shown in Figure 4 to 10. The distance the whale moves between the first and second positions is represented by the length of the line segment between P1 and P2, written P1, P2. The whale's displacement is indicated by an arrow drawn from P1 to P2, labeled P1, P2. Displacement is a vector quantity because it specifies both distance and direction. Distance is a scalar because only the magnitude of the displacement, a single piece of information, is given. If the whale moves on to P3, the total distance that it traveled through the water from P1 is the sum of the distances P1, P2, and P2, P3. Since the total distance is length alone, it is still just a scalar quantity. The whale's total displacement, however, is the vector from P1 to P3. See Figure 4.11. The length of this vector is clearly different from the distance that the whale traveled. Vectors cannot be added simple arithmetic. Fortunately, vector addition is not difficult to understand. You will learn this important skill in Section 4B.